So let's do an example here in which we imagine that we've got a charged mass hanging on a thread. So let's say that this mass right here is going to be 65.5 grams. And let's say that it has a charge of 18.4 microcoulombs. Okay. And so what I'm going to do is, as it's hanging there, I'm going to activate an electric field going to the right. Okay. And when I do that, I notice this thing swings over to the right, and it swings over a distance or an angle of 22.4 degrees. So the question is, how strong was that electric field? Okay. Well, so free body diagram. We got tension. We got mg. We've got the electric force. Okay. So this angle right here, theta, is 22.4 degrees. So we look at that and we say, okay, so this component balances that component. Okay, so T sine theta is equal to the electric force. T cosine theta, so that component has to balance this component, has to equal mg. So if I divide the two equations, T sine theta divided by T cosine theta, that's going to be equal to F sub E over mg. The T's cancel, so tangent theta equals F sub E over mg. Well, I know that the electric force is going to be Q times E. Okay. Now, really, I know that, the electric force is vector QE, and so that means that if Q is positive, the force is in the same direction as the electric field, and so that makes sense. Okay. And so that tells me, therefore, I can plug that into the equation that I just had, because the equation I just had said that, tangent theta, okay, is going to be Fe, so that's going to be QE divided by mg. Well, I wanted to know how strong the electric field was, so it's really simple. I just solved this equation. So mg tangent theta over q. Okay, so I plug in the numbers that I had, 0.0655 kilograms. Remember, we got to convert back to the base units, 9.81 meter per second squared times the tangent of 22.4 degrees. Okay, and then I divide that by the Q, which was the 18.4 times 10 to the minus 6 coulombs. And so that gives a final answer of E equals 1.43 times 10 to the 4th Newton per coulomb. Okay, so there we have an example. So that's our first example here of just a mass hanging on a string. Okay, now, important thing here was that the charge, Q, was a positive 18.4 microcoulombs. So, as it was hanging here, when I put the electric field this way, the force was that way and it swung to the right. Okay. What would have happened if instead Q was minus 18.4 microcoulombs? So what would have happened in that case? So same thing, it's hanging here. I exert a force to the apply an electric field to the right. What happens? Well, we know that the force is QE. Okay, so Q is negative. That means the force is negative. What does negative mean? It means, remember, all the way back to Physics 1 when we talked about vectors. Okay, so this was chapter 3. A negative vector means a vector in the opposite direction. So that means the force would be that way, and so that means this thing would swing into the electric field. So for a negative charge, the force is in the direction that the electric field is coming from. So for a positive charge, the force is in the direction the electric field is going. So for a positive charge, it's swinging with the electric field. For a negative charge, it has a force into the electric field. So that's a very important sort of point here. When you're doing homework problems, that's something to keep track of, that negative charges have a force into the electric field, not in the direction the electric field is going. They have a force that's opposite.